Okay, so return our problem. Actually, there is a problem in our account, so I have just been kicked out and go again. So sorry for this inconvenience. Do you all already attend, right? So, okay, we are here. Previously, I talked that the VA, right, is equal integral of EDA. The first type, EDA, the same, vector E and vector dA have the same direction because the previous solution we have. So we don't need vector here. Okay. And then because the vector, because electric field is the same on the side one of the cylinder, so its value is constant. This means in this case I have the integral of E dA, right? Because it's a constant, so I move electric field from the integral outside. And after I move that, we only have integrate on just for the area. So the problem now to be a problem that we need to determine the area. The area of cylinder is very easy to determine the area of cylinder, right? Look at here. When we calculate the area, the side area of cylinder, please remember I cut this cylinder is same as a can. It's same as a can, right? So I cut along the exit here, and I open it. I cut it and I open it. Can you see? When I cut it, I open it. I cut it and open it. So it should be a rectangular. It should be a rectangular shape. So it's the easiest for you to calculate this area. So in this area, the length of this area is 2 pi multiplied r, and in this case it's L. Okay, L is the length, the height of cylinder. So that's why you have the area here, and this is from Gauss law. So you can determine here the value here. This value is the 2 ke lambda r, right? This that's value, this value. Okay. Question. So in this case, means that we already determined electric field. Okay. And in the first case, they assume that the diameter is 3 centimeters. You have the cylinder with the diameter. Sorry, you have a rod. You have a rod with a rod here, a long rod. with the radius is 5 centimeter, right? But in first case, they ask you to calculate the electric field at the distance of 3 centimeters. It means this point need to be inside the cylinder. So what it means? It's inside cylinder, so you can choose the Gauss surface. The Gauss surface here. The distance is just 3 centimeter. Okay, just 3 centimeter. And remember that it's the same as previous problem. Inside the cylinder, there's no charge because there's nothing inside the cylinder. Inside the cylinder is empty, so there's no charge. This means that in this case you have electric field equals 0. Yeah, you're right, Ding Dong. You're right, because there's no charge inside. Same as previous problem, we already saw inside there's no charge, no electric field. But in outside, you can substitute R to here, and you will obtain the electric field for the outside case. As long as it's larger than 5 centimeters, you can determine the electric field. It's the same. It's the same for the case of 100 centimeters. It's okay. And to determine the direction of the electric field, you need to know the side of the charge. In this case, they give us lambda positive, right? So on electric field you determine outside the cylinder, the rod, outside the rod should be your hour, should be have the direction of hour. So that's the problem 37. Any question? If not, please go through this. Go through the 38 problem. In this problem, they give us a schematic, a figure 24.38. This is the schematic that determine electric field, as a function of radius. Okay, electric field as a function of radius. So the answer that why is the following situation impossible? They provide us information that the following situation is impossible. So, but they ask us why, we need to explain. They give us a solid copper sphere with radius 15 is in electrostatic equilibrium and carry a charge of 40 nanocoulomb. This figure shows the magnitude of the electric field as a function of radial position R measured from the center of the sphere. Okay, look at here. Look at this. This is from this figure. I just try to remind you it's from your theory lesson. This is for the sphere, but the solid sphere, not the empty sphere. This is the solid sphere. It have this is the solid sphere. It's not same as this one. This one, what did they give us? The charge of 40 nanocoulomb. Alright. Okay. So in this case, you can see from the radius from 0 to 1.5, I passed that. 1.5, ain't no charge. It means that this is the empty sphere and this is the solid sphere. It's different, right? Okay, this is because it's a solid sphere, so inside the sphere we have the way we can calculate the electric field. The electric field is increased as the radius increase from here to here. Okay, from here to here. And outside the sphere it decreases. So we can see this same curve here. This is for outside the sphere, right? But inside is different because this is a solid, this is empty. So when you look at two figures, you can question that this one is for the empty sphere and this one for the solid sphere. Okay. But the question is that why is the following situation is impossible? If we want to know, we need to calculate. How to calculate? You just calculate the electric field on the surface of the sphere, and you will know the situation. So how to calculate it? We already know previously. Remember, I already did you how to determine. Not yet, right? Not yet. But for the sphere, it's very easy to determine. I will guide you here. To determine the electric field here, you need to choose the Gauss law. Okay, I'm not good painter. Okay, this is the Gauss law, right? Gauss surface, right? Gauss surface. You chose Gauss surface here, and remember that we have the charge is positive. So we have electric field on a surface in this direction, and also if we want to determine electric field here, we also have vector dA. Vector dA also have same direction because usually it is perpendicular to the surface, right? And it's usually go to outward. We rarely choose this go to inward. We choose to outward. Okay. And you can apply the Gauss law. The Gauss law gives us Phe equal integrate E dA equal sigma Q divided epsilon 0. And remember that in this from the speaker we have dA and E have the same direction. It's okay, have same direction. And so we don't need vector here because it's the same direction. So we have E dA, and this is total Q, total charge divided epsilon 0. And because this is the symmetry sharp, because we have the symmetry sharp of the sphere, so the electric field on the sphere surface should be the same. When it's the same, the only thing we need to do is we move E outside. Okay, so we have E dA equal total charge divided epsilon 0. And here you need to calculate. You only need to calculate the area of a sphere, of surface of sphere. So how much can everyone give me? How much I will have here? Someone need to answer. Maybe next week I will download the list of attendance and call your name. Is that a good way? Okay, just help me. Just help me. Just have to provide the areas of the sphere here. Student, how to calculate this one? This is the area of the sphere here, right? How much you can obtain? Are you still listening to me? Are you okay? Thank you, Nguyễn Tiến Dũng. You should message publicly so everyone can look at it. Nguyễn Tiến Dũng, thanks for your comment. But you need to write it publicly. This is very simple, right? 4 pi r square. So you have E 4 pi r square equal total Q epsilon 0. You have total Q here, so you can determine E equal Q epsilon 0 or pi r square. And then, okay, you have the result here. Because once they give us KE, because this is 1 by 4 pi epsilon 0, right? So it's same as our result. And they substitute on value of R, Q. This one is KE, so they substitute KE and they obtain 1.6, 116 kilonewtons per coulomb. And look at the figure here. In the figure here, the maximum value of electric field just around 6.2. It means that it's less than 8 kilonewton per coulomb, right? So the impossible thing here is the maximum electric field is too slow, too low as compared to what we calculated. As compared to what we calculated here, it's okay. So that is the impossible thing. Okay, question? If not, we move to the next problem. Yeah, 4 pi. Yeah, the area is 4 pi r square. You're right, Daniel. Question? Any question? Okay, we move to the next problem. Do you have any question for this problem? If not, we will move quickly. Today we try to finish on the problem. And next week we will go to next chapter. Do you have any questions relating to this problem? No? Level we know. We're very good. How about our students? Do you have any question? Thanks so much, Trần Cao Nguyên. Yeah, very good, very good, very good. Okay, how this problem? The question is long. All students, next week you will study normally, but next week you will have the midterm. Next week. I mean the next 2 weeks. Next 2 weeks you will have a midterm. It's okay. Next week you study normally, but next 2 weeks you will have a midterm. I will inform in your I will inform formally on your system. Do you have any question related to this problem? Did you read this at home? Remember that when I give you a midterm, it's very easy for you to do. It's the thing is I will upload at that time. I will provide you a question, and then you download the question or the problem into your computer, and then you solve it and you upload it onto the system. I will limit the time for you to upload. You just solve and upload your answer onto the system. And I encourage you to just to write by hand, because it takes a long time for you to type some formula. So the best way for you to write, you write down on a paper, and you capture a picture and you upload on the system. How do you think that method is stable for you? I think that's the best way for you, right? Hello? Hello, everyone. Please let me know what you're thinking. Yeah, thank you. Thank Nguyễn Hoàng Hồng Tâm. So that's the best way for you. It will save your time, and you have 1 hour to do your exam after the hour. So after the hour, the class is stopped, but you will have 1 hour to do that. I intend to give you five problems, but you only need to solve 3 problems. You can choose 3 in 5 problems. So if many students have the same chosen, there will be a problem. Maybe you are copied together. And remember, I know your writing. So if someone copy another solution, if someone copy a solution from another student, there should be a problem with you. I know that. So please, although this is online, the online exam, the midterm exam, the time flexible for you, the place is flexible for you, but don't cheat me, okay? But don't cheat the exam. Try to do your best. I will provide you 5 problems. You need to give me 3 solutions of 3 problems. Okay, you choose 3 in 5 and just solve it in 1 hour. Is it good for you? Okay, thank you. That's the way we do. About all the students that didn't attend our class, if you can help me to inform them, I feel very thankful to that. It includes the first chapter to now, to today, to next week. It means it's covered from the chapter 23, maybe to 25. Hope that next week we will finish the chapter 25. So it's been good. I will cover. I will limit the ranks. I will limit the chapter that you studied later. Okay, I will inform you formally. If you know all the students in our class that didn't attend today's live class, please help me to inform them that we will have a midterm next 2 weeks. We will have this. Please help me. Thank you. So relating to this problem, do you have any question? A long straight white surrounded by hollow metal cylinder whose axis coincide with that of white. The white has adjustable unit length of lambda and the cylinder has an adjustable unit length of 2 lambda. From this information, you got slot 5, 8, the adjustable unit length on the inner surface of cylinder, B, the adjustable unit length on the outer surface of cylinder, and C, electric field outside cylinder addition are from the S. Actually, this question is same as the previous question, right? The different thing we have here is that we don't know the number. We don't know the number. We just so in this case, we just need to obtain the formula. That's all. And the situation is same as the previous question, previous problem. So if you have a question for this, you have no question for this problem, I will pass it. You move through it. It's okay. Yeah, I will help you to draw the figure here. And you need to just try to read the solution and understand it. Okay, question? No? Yes? Please let me know. Are you listening to me? Are you sleeping? Okay. If you have no question, I will move through this problem and go to this one. About this one. Do you want me to have this solve this problem? Student? Actually, this is not easy problem. We have very complicated system. They provide us the configuration shown in figure 24.54. Suppose APC. Furthermore, suppose the electric field is 0.10 centimeter from its sensor measured to be 3.6 multiplied 10 power 3 newtons per coulomb. Readily in what happened with our I think there is a problem in our account. Why? This is the commercial account, but they apply the limitations of 40 minutes on our schedule. I don't know what's happened with this account, but try to finish it before it's closed. It will close in 10 minutes, so we try to finish in 10 minutes. Okay, student? Okay, I feel that only me have a solo performance. I need your reaction. You feel Please let me know what you feel. Sometimes please let me know. Okay, or I understand, or I don't agree. Sometimes you just need to talk that. I need to know what is your response. Okay, so we have the communicate situation configuration here. We have a sphere. We have a sphere put inside a insulator sphere. The insulator sphere. Remember, for the problem under sphere of the charge sphere, you have two cases. Two cases. You will have two cases for a sphere. The first case is a conductor sphere. A conductor sphere. And the second case is the insulator sphere. Please remember that if we have insulator sphere, the charge will distribute. The charge will distribute uniformly inside the sphere. But for the conductor, when you have the conductor, even you have the solid conductor, conductor sphere, inside of the sphere have no charge. All charge will move out the surface of the conductor sphere. But in case we have the insulator sphere, the charge will distribute everywhere, inside and outside sphere, and inside and on the surface of sphere. Please remember that. It means that in for case insulator inside the sphere, you have a charge. Okay, but for the conductor sphere, inside the sphere, for example here, is no charge. Even if a solid, the inside is not empty. For the conductor, remember, for the conductor, inside not empty. It's a 3D, a 3D, a 3D shaft. 3D shaft. It's not empty, but inside no charge. On the charge, we move out the surface of the conductor. Remember that. Okay, come back to our problem. We have here insulator is mean that charge distribute everywhere inside and on the surface of the insulator sphere. Okay, and for this one is a conductor. So a charge will distribute on the surface here and on the surface here. Inside the conductor is no charge. Okay, no charge. So here they ask us from this information, find the charge on the insulating sphere. So what they give us? They give us the radius. They give us the electric field. Oh, they give us electric field at 0.centimeter from the sensor. So we have A5. So this means 10 nanometer here. It's right because from P20 from here to here 20. So I think that is the 10. So they give us electric field here, and the distance is 10, right? They give us, this is the reverse question. Previously, they provide us a charge and they ask us electric field. In this problem, they provide us electric field and they ask us charge. So we need to apply the Gauss law here. That's all. How to apply this? Please look at here. So we apply at the point with a distance 10 centimeter from the center here. Okay, apply 4 point here, and we choose the Gauss law here. We know the electric field. We know they keep us the radius inward. Okay, electric field radically inward. So inward. So electric field inward, right? Electric field inward. And for the case A, so we apply the Gauss law here, right? And we know that this one and this one have same direction, so we don't need it. So we have E and integral of the sphere surface, and this is the area of the sphere, and here is total charge inside. So for the case smaller is larger than A from here to here, and smaller than B, it means in 10 centimeter. 10 centimeter is agreed with this case. We can apply, and we have Q, the value of Q here. Question for question A. Any questions, student? And for the question B, the net charge on a hollow conducting sphere and the charge on inner surface of hollow conducting sphere, and D, the charge on outer surface of hollow conducting sphere. Yeah, we have two things. We have to another two things we need to do. The net charge on the hollow conducting sphere. So we will apply the point that the electric field at the point 50 from the sensor is with the magnitude and point hour. So it means in this case it fits with this case, right? We need to choose. Okay, we need to choose the Gauss surface here. We applied the Gauss surface here, and we assume that inside the Gauss surface we have two charges, two materials that have charge. The first material is insulator sphere, and the second material is a conductor. So we have Q and Q dash. We have Q and Q dash. Okay, we apply the same equation, the same formula with the Gauss laws. We obtain here. Okay, and we can obtain Q. In this case, because E go outward,